So, welcome back everyone. We are studying the NPTEL course on topological phases of matter, and in this chapter we are studying symmetries. And in the last class we introduced many types of symmetry, and the one we emphasized more are called anti-unitary symmetry. And one of the feature of anti-unitary symmetry is that as you apply twice, here A is an anti-unitary symmetry, as you apply twice you can get back to the same state in the case of A square equal to plus 1, or in the case of A square equal to minus 1 you get back to the same state with a different with a pi phase difference. And we just introduced the idea that in this case where A square equal to plus 1, the state is also an eigenstate of the operator when A is a symmetry. So, that means A commutes with H. In this case, second case, when A square equal to minus 1, even when A commutes with the Hamiltonian, we will see that A psi and A psi are no longer the linearly independent, are no longer the same state as in this case, rather they become orthogonal to each other and they are degenerate. So, as long as the Hamiltonian goes, they have the same eigenstate. So, today we will prove that so the state we are interested in are the eigenstate of the Hamiltonian, and this is a Hermitian Hamiltonian with the energy eigenvalues being real. Right. So, now if I multiply a general operator A, okay, let me rather use an operator O, which can be anything, unitary, anti-unitary with O square equal to plus minus 1. Right now I am taking it to be general. So, multiplying from the left, so this is a number. So, O acting on E will give you E star if it is antilinear, or E if it is linear, and because E are energies are assumed to be real. So, for both cases we get this. Okay. So, now we also assume that they commute. So, which means we can just change the order, and that is what it gets. So, that means if psi is an eigenstate of the Hamiltonian, O psi is also an eigenstate with the same eigenvalue. Okay. So, now two cases can happen. Case 1 is when O acting on psi gives you back the same state with a constant coefficient. So, that means this is also an eigenstate. Okay. So, in this case acting it twice, you will get alpha square psi, and since O square has to operating a discrete symmetry twice, we are supposed to get back to the same state. So, which means right, and by definition this has to be greater than 1, greater than 0, and so this gives us, because O square equal to plus 1, this gives us the only choice that either you start with this, you will get this, or you will start with this, you will get this. So, for this case, when O square equal to plus 1, H commutes with symmetry operator already gives us the fact that psi is also eigenstate of the operator. They are just the same state, if you like, just moved little bit with a constant factor. In the case of O square equal to minus 1, what happens? Okay. And now we do it for anti-unitary operator only. This still holds. Okay. So, now let us consider the case for O square equal to minus 1, which is only true for the anti-unitary operator, and in this case we again start from equation 2 and compare with equation 1. So, both are state with the same eigenvalue. So, one possibility is obviously O acting on state gives you back the state which we are just considered. The other case is this state and these states are orthogonal, and this is going to be the case for this. O are orthogonal. So, that means the Hamiltonian will, all eigenenergies will always be degenerate. So, let us show that. What we want to show is O and psi is 0. That is the definition of orthogonal. To show that, let me start with a different state, and then we will substitute phi equal to psi at the end. This is equal to, as we have studied, under a symmetry, it changes bra state to K state, or gives the complex conjugate, right? That is the definition we studied. So, if I apply O again, so I am supposed to then get O phi O psi. So, this is O square, and I am going to use minus 1. So, minus, So O square equal to minus 1 psi. So now let us substitute phi equal to psi. So what we get is O psi acting on psi is equal to minus O psi acting on psi. So something that is equal to its minus of that is only possible when this itself is 0, or if I take it to this side equated it will get to 0. So which means O square equal to minus 1 always lead to the fact that orthogonal, and for the Hamiltonian case they are degenerate. This means psi degenerate for the Hamiltonian. So every energy eigenstates will then be degenerate for this case, and this is called Cramer's degeneracy. Okay. So this is the distinguishing fact about anti-unitary operator with O square equal to minus 1. What will be the example which will show? It turns out to be time reversal symmetry is anti-unitary, and among them for the case of spin half or odd frequency or odd multiple of spin half, it will be always minus 1. And we will prove that. So the other two remaining types of symmetry are symmetry and anti-symmetry. So the symmetry is when this, and anti-symmetry is when Hamiltonian commutes with some operator. Let me call it O. Anti-commutes with this. So here the symmetries will be inversion, time reversal, and reflection, and other symmetries which we will not consider here. For example, discrete rotational symmetry, continuous symmetry, they are all like this. Whereas the chiral charge conjugation symmetry are anti-symmetry. So I am using the word symmetry and anti-symmetry together. It's just a matter of nomenclature. This is symmetry as we often just attribute this to be, except the fact that this operator anti-commutes with the Hamiltonian. So that's what I am rather going to call it anti-symmetry. And if that happens, and I am studying some energy eigenstates of a Hamiltonian, and if I apply anti-symmetry, and anti-symmetry can be can be both unitary like chiral or anti-unitary like charge conjugation. So, because energy eigenvalues are real, so I can slide it to the right hand side like this. Now, these two anti-commutes, so we are supposed to get a minus sign, and I have taken that minus sign to here. When A is an antisymmetry of the Hamiltonian, for every state with energy eigenvalue E, there will exist a symmetry multiplied with that state as an eigenstate of the Hamiltonian with minus E energy. So, for every energy E, there must be a minus E energy as an eigenstate. So, this is the reason these are also called particle hole this particle hole symmetry is sort of used by different people in different contexts. I would generally call a particle hole symmetry when there is an antisymmetry, which can be both unitary or anti-unitary, but in some references and books the charge conjugation symmetry are exclusively called to be particle hole symmetry, whereas chiral also gives you, for every energy there is a minus E energy, and it also gives a particle hole pair of every energy, but it is just a misuse of the nomenclature to call charge conjugation exclusively as a particle hole symmetry. The final one is does not require much time, is called proper and improper rotation. It can be for any other symmetry, but let me just focus on the rotation. So, let us say I have some 2 dimension or 3 dimension, and I have some point here, and I have minus r here. So, there are 2 ways we can go from a state sitting at plus r to minus r. One is by making a rotation by (180°). So, that is the C2 rotation, or I can just take all r, x, y and z coordinate and just flip the sign, that is the inversion symmetry. So, its proper rotation are when the determinant equal to plus 1 and C2 rotation is one such example, and C4 and every other thing, whereas improper rotation is, for example, inversion. Reflection, and in principle time reversal also, but time reversal is only t goes to minus t. So, alright. So, this concludes all the type of symmetries that we need to worry about and especially the discrete symmetries. Okay. And now we will try to see how all these symmetries manifest in condensed matter systems for different states and for different Hamiltonians. And we will do it in two ways or rather four ways. One is with first quantizations, and then we will do it in real space and momentum space. Then we will move on to second quantizations, because second quantization is a very popular methods to study condensed matter systems, and in which case again we will do it in both real space and momentum space, and we will see the key differences between first quantization and second quantizations, and also the key differences between real space and momentum space. So, the first thing we will study is first quantization. So, one may wonder why things are different as you go from first quantization to second quantizations, because this is nothing but just a way to represent or write the Hamiltonian in different forms, right. So, why should the symmetries should change? So, again none of the physical properties should change. So, the expectation values, inner product, they should remain same, and they are same. So, the symmetry action on the state and the operator in the abstract space, they are uniquely defined for a given symmetry. But as we choose a first quantization or second quantizations or real space, momentum space, what we are choosing is we are choosing different representations, different states to represent that system. And as we choose different state or representation, the corresponding operators and Hamiltonian are also written in the representations, which will also look different, but their inner products and expectation values are same. In that case also the operator, the symmetry operators we write in different representations will also look differently. And how would they transform from one state to its symmetry transformed state is what we want to study. So, there are two types of symmetry. One is space time or the manifold symmetry, and other one is internal symmetry. In a given space time, if you rotate the basis of a fiber, how things transform. Okay. So, let us say I have some manifold and I am taking two base point, some Q and some P, and in which I have the fibers. Let us call it psi. Prime here and psi. So, the space time symmetry will take me from this point to this point. For example, inversion would be from this point to this point, and rotations again will be from this point to this point by making some rotation and so on. Whereas, the internal symmetry will be staying here, but let us say this state is written in some frame and we make some changes in the frame, because you remember that the principal bundle, the states, the fibers are some structure group like U1 or SU2 and O3, On, this sort of state. So, as you make some changes, if you have a SU2 symmetry, when we talk about spin, we will see that as you make some rotations in the spin, then nothing changes. So, that will be the internal symmetry. But even if I make a space-time symmetry, changes from P to Q base point, how the state in this spatial transformation also changes, there will also be representation of that symmetry for the fiber. So, what I said, inverse transform into, and let us choose some, at this point we chose some coordinate system to some chart R, and that is my R prime, or let us call it R prime, and at this point we choose some chart which is some point R, and this is some point R prime. Okay. Remember that this belongs to some fiber, some frame. So, that means there are two symmetry operations we have to worry about. How psi and psi prime are related to each other as we make a as the spatial point or base point is rotated, and as you make this rotation in the base point, how the fiber will change. So, there is a unitary or anti-unitary operator that will rotate the state in the frame basis. Okay. So, we need to think of this two things. So, let us take some examples. So, inversion symmetry by definition, I have some R and I want to go to minus R. Okay. So, let me just focus on the space and define some vector which under inversion, so I am calling it inversion I, changes to minus x, minus y, minus z. So, what sort of operator that can make this happen? So, I has to then be a, so that is equal to minus x, y, z. So, I must then be a diagonal one. So, it is acting on x, give you minus x. So, this is minus 1, 0, 0, 0, acting on y gives you minus y, 0, 0, 0, minus 1 in the spatial coordinate. It is very easy to see now that x square equal to minus 1. Sorry, I made a mistake. Right. So, I have not used the state yet, this is just in the position. If I define a vector, This is how any vector will transform. Okay. So now this is in 3D. Now you can imagine what will happen in 2D. Let me use a different color. X, y. So I have some point r equal to x, y, and minus x minus y, right. This will be our common sense of defining the inversion going from r to minus r. So we will have x, y goes to minus x minus y by an operator minus 1, 0, 0 acting on x, y. This is my inversion. But now you see there is a trouble. Now the determinant of identity is plus 1. So it becomes a proper symmetry. So this means this going from here to there, that cannot be our inversion symmetry in 2 dimensions, and this is true for any even dimensions. So in even dimension there is no such thing like an inversion symmetry. Okay. Inversion symmetry is only defined in odd dimensions. So in 2D, even if somebody is saying it, inversion symmetry, it should rather mean a reflection going from here to there, in which we change minus x, y remains same, or from here to there, in which case it will be x minus y. So in this case one of them will be plus, other will be minus. So then it becomes in. So then in 2D, inversion is only reflection. But in odd dimensions, inversions are well defined. So let us go back to 3D. Let us do it in 3D. So under inversion, then r goes to minus r by definition. So p, which is a momentum, in classically this is just dr by dt, that will also go to minus p, momentum. Electric field goes to minus e, whereas magnetic field remains invariant under inversion. So angular momentum remains unchanged, and this is because it is a product of r cross p. So because both are changing sign, so L remains invariant. And since spinor generally do not have a representation in space time, because it is a local rotation, but it always transform as the angular moment, as the linear angular momentum. So with this logic, you can also say that spin remains unchanged, and that also gives us the logical conclusion that magnetic field remains unchanged, but electric field changes. The state, how that should change under inversion, or rather what is the corresponding unitary operator for the inversion. So this sort of notation tells you that it is an abstract state, it does not have any space time. But if you write it in some representation, so let us do it in position. So this is by definition psi x So, so then psi prime is equal to p times psi or inversion I or ui it's good idea to do it for once or twice, and then we will rather there is a number. This by definition changes to a state at minus x. Okay, I am going to do it twice, so let me just do it once. So either I do it in the space time, and this is just a scalar number, so I will just keep it to be like this, or I can act it on the kth state and not do anything to the eigenstate to the wave functions. Both will give us the same result, and this is by definition minus x. And that is equal to, if I just take this one, so the conclusion is under inversion psi x changes to psi minus x if there is no unitary operator acting on any basis. So, I am just assuming that there is no change in the frame. If there is a change in the frame, that also changes also has to be incorporated, and that we will talk about later. Okay. So, this is in the position space. Now, if I do this in the momentum space, again the procedure will follow. And now acting if you follow this, the same procedure. So, inversion acting on momentum will give you minus momentum, and what you will find is that the wave function under inversion changes to the wave function localized at minus p. So, we took the example of inversion and demonstrated how the state will change under inversion, and in the next class we will maybe we will take two more examples. One is the parity and time reversal symmetry. Okay. Thank you very much for your attention.